So let me start with a few acknowledgements. First, let me thank Hargav and Jacob for putting together this whole special year. And I guess I should thank them and Kęstutis for putting this workshop together. And IES for hosting all of these events and the opportunity to speak here. I also wanted to shout out the crew, I guess this is Martin and the other PIs of the New Simons collaboration. I think that's a great development that they've gotten this big grant to support work in this field, and I look forward to some of the results of that. And finally, I'm supposed to remind myself that I'm giving this talk on land of the Lenni-Lenape indigenous people. So this talk is a little bit retro in that I'm not really going to use any technology from the last 30 years or so, but I think it's timely because some of the questions I'm going to raise, I'm hoping modern technology does have something to say about it. So first, let me start by telling you what I mean by algebraic Frobenius structure and also algebraic Frobenius pullback, which will give meaning to this notion. And then, so the structure of the talk is that I'm going to do this setup, and then I'm going to focus on two classes of examples that kind of will illustrate the somewhat vague questions that I'm going to raise. So there'll be a lot of question raising and essentially no question answering. I mean, except that if you actually ask questions, I will try to answer them. But in terms of mathematical, so you're welcome to ask questions, and I will do my best to answer them. But I will raise the questions that I'm planning to raise are a little bit ill-formed, and part of the point is to understand what really is going on. So, but the basic setup, hopefully, this part it should actually be formal mathematics. So we should ask questions if you don't understand. Okay, so I'm going to start with a perfect field of characteristic P, which you can imagine is finite for most applications. You could even imagine it's FP for the applications I'm going to be talking about later. Curly X is going to be a smooth p-adic formal scheme over WK. So if you want, you can imagine the completion of something algebraic, because again, all of my examples will eventually have that form. I want to set things up. Generally, Z is going to be a relative strict normal crossings divisor, which for the moment you can assume is empty, but I want it to be non-empty to talk about examples. Okay, so the fundamental object in this part of the talk is some category of modules with a connection. So I'm going to write MIC, which is shorthand for modules with integrable connection. So the category MIC of curly X and curly Z will consist of pairs curly E, which I don't have a good fractor font in my handwriting, so that's the best I can do. How about this kind of fake frac E? Maybe that will make it a little bit more frac E. Let's move this a little. I don't have good font control in my handwriting. So this E, so the frac E is going to be a coherent sheaf on here, and nabla is going to be a connection. So nabla is going to be it's going to be a WK linear integrable. So the connection, the curvature will be 0. And I want to allow it to be logarithmic. So I'll say Z logarithmic connection on this sheaf E. Now I said coherent sheaf. If I was doing this in a situation where P was inverted, then this would be forced to be a vector bundle by the existence of this. Now in general, I don't always know that I can, if I start with something with p inverted and I have one of these data, I don't always know that I can actually pick a vector bundle with these properties. So I'm going to allow coherent sheets, but you should morally imagine this is more or less a vector bundle. And that's literally true after you invert p.
So that's log differentials with respect to loss.
Yeah. So z, I wrote z logarithmic to mean, so yeah, this should be allowing, well, not arbitrary poles, but log poles along.
Yes, but then it does not need to be locally free characteristic 0. It could be just.
That's true. That's true. With the log connection, it can be more complicated. So, but let's just say coherent. I don't think I need anything stronger than that. So, oh, and I want to do one other thing, which we'll see why in a moment. I'm going to assume p is a prime not equal to 2. Because theorists always say 2 is the oddest prime, and p equals 2 will be a little bit odd in the following statement. So I'll call this a proposition definition. And so this says that there is a functor like this, which I'll write fp upper star suggestively, even though it's not actually the pullback induced by a morphism, but nonetheless there is a functor from this thing to itself with the following properties. So first, so this category has some natural structures, which I want to respect. The tensor product and the internal Rham. It also is kind of compatible with at least étale-based change on X. Formally étale. It's actually a little bit stronger than that. You can also do, so for example, if Z is empty, you can also do closed immersions. So you could kind of upgrade to formally unramified, but let me just say it this way. And this is the key point. So in general, this X may not have any lift of Frobenius, or if it does, I mean, locally it will, which is why I put in condition B, but if it has a Frobenius lift, it will have lots of them. But and let's say, well, I should say what a Frobenius lift is. Let's say an absolute P power Frobenius lift. So I'm going to say sigma is a Frobenius lift on X, which also carries Z into itself. So I need that to be able to work with the log differentials. So there's a natural isomorphism of this thing with the actual pullback by this thing. And okay, maybe I should say a little bit more to, well, but let me write it, let me show you what this construction is, and that will kind of show you that this object is somehow canonical. I think probably I need to say something like, well, these isomorphisms are compatible with, I'll show you what isomorph, right? So the point is that there are isomorphisms. The point is that given two Frobenius lifts, sigma 1 and sigma 2, there is a totally canonical natural isomorphism of the pullbacks by sigma 1 and sigma 2, and it'll satisfy the cocycle condition. So once you know this, then you can sort of locally define the pullback to be one of these, and that's unambiguous because you have natural isomorphisms to turn you around. And then you can glue back together. So the point is that this happens. And why does this happen? Well, the point of this is that, the notion of a connection is there to give you some notion of parallel transport. And two Frobenius lifts are necessarily kind of close together because they agree mod B. And so you can use that kind of canonical parallel transport to define this isomorphism. So concretely, write this isomorphism down. Again. So I'm claiming this natural isomorphism between the phi1 sigma 1 pullback and the sigma 2 pullback. Write this down using Taylor series. So let's assume I have some automorphism, I guess formally automorphism, I should say, complete from X to formal, let's say formal affine space and some coordinates. Coordinates x1 through xn. P. Right, so that means that the module of differentials is going to be generated by, it's going to be freely generated by dx1 through dxn. And I also have corresponding basis of derivations, partial derivatives with respect to these variables. The dual to x1, xn, those generate the differentials. And so the Taylor series description of this canonical isomorphism is that if I have some element of the pullback by sigma 1, so I'm going to write the tensor over sigma 1 with 1. This is going to map to sound. So I'll write I underscore the multi-index I 1 through IN. So I take some partials of this V, and then over here I have 1 over I underscore factorial. And now this bit, let me actually write this part out. It goes from 1 to n. I take the difference between the effects of these two Frobenius pullbacks on xj, raise this to the power I sub j, and I notice that this is divisible by p.
What's the object of X's mapping to again? Like
X is, sorry?
the target of the automorphism?
Oh, it's the formal affine space over WK in the variables x1 through xn. So the point is that if I have this automorphism, then these things form a free basis of the differentials. So I can write everything in terms of, I can have access to this dual basis of partial derivatives. So these are the partial derivatives showing up here. So, right, their action is the action, right, so I should really write, you contract one of these things with the connection, but, so this is contract with the connection. So I'm secretly doing that here, but I'm not putting it in the notation.
Presumably some of the x's correspond to the divisor.
Yeah, sorry, I want to specify, because I have these log structures, I want to make sure that, yeah, I need to assume, I also need to assume that Z is the pullback of the zero locus of the product of some subset, yeah. Well, so the point is that I need, right, so the property that I'm acting, so I should say, and this is also going to be divisible by xi if xi cuts, maybe I should say, maybe just say it's divisible by p and by xi, right? So, right, if I'm actually preserving this divisor, then this thing, each of these things will also vanish on that divisor. So, yeah, so this will, yeah, because you're going to introduce these, you're going to introduce a pole along that divisor, but this part will clobber that.
It has nothing to do with Frobenius specifically. It's any morphism of the special curve of which.
Yeah, it has nothing to do with Frobenius specifically. Yeah, this is just because I have a map from the special fiber to itself, and I know that there exists lifts. So yeah, so I'm not using, right, so the only thing I'm using is that I know this is always going to be divisible by P. Okay.
Sorry.
Yes.
Get confused. So you don't assume any sort of nilpotence on connections.
No, so I'm not, for instance, assuming, yeah, so I'm not, maybe this is a remark. I'm not assuming any sort of nilpotent P curvature condition. If I did, that would make this easier, and in particular, it would solve the problem with P equals 2. But I actually want to apply this in a range of families, and I'm not where this condition isn't going to be satisfied everywhere. So it's actually convenient to not have this condition.
Question. So
yes.
what is V?
I'm sorry. Oh, V is just some section. V is some generic section of some section of the bundle. Oh, sorry, it's frac. Right, so the pullback, right, the pullback by sigma 1 looks like, kind of tensoring over the structure sheaf with the structure sheaf via Frobenius. So this is just some generic, that's just some generic section of the original. Okay. So we've already started with remarks, so let me give you another remark. With more work, you can show that this thing is fully faithful and it reflects sub-objects. That's not so obvious from, a priori, it's not so clear that I don't introduce. So this morphism is set up so that if you start with a horizontal section, you've got a horizontal section. But it's not clear that you're not producing more. You could show this with some, well, the way I know how to do it is to use some basic facts about fields complete with evaluation and carrying a derivation, stuff I wrote out in my book on p-adic differential equations. You can presumably write down a proof in a different style if you prefer. But this is somehow saying that if you, I won't make a precise statement along these lines, I'll just mention out loud. This is saying something like if you apply this, it preserves some sort of Tanakian automorphism group.
Don't you have to assume that is vector bundle for this statement, rather than if it's
For which
skewed
one?
by p, for example?
I'm sorry?
If it's skewed by p, is it?
Oh, yeah, maybe I should say this is on torsion-free objects. Torsion-free objects. Yeah, sorry. I'm kind of thinking of this, maybe what's better to say, on the isogeny category. Yeah, essentially, if you, if you invert P, that's what I mean. Yeah, so kind of ignoring the possibility that, yeah, you might have unallowing torsion. Right, when I apply this, I'm usually going to be applying it in some situation where I actually have a vector bundle in connection, and I just know that it happens to admit some lattice. But I don't want to fix the lattice in the data. Okay. Another remark. So because of how sort of generic this argument is, this also applies in families. Parameterized by some p-adic formal scheme. Now I have to write another frac layer. Let me just call it S and not try to write it in frac. But there is a catch. Well, it's not that it provided that, it's just have to notice one thing. What I'm doing with a Frobenius, right? Frobenius pullback, this kind of local Frobenius pullback is not WK linear because it's an absolute Frobenius. It's only WFP linear, ZP linear. So if you try to make a statement like this, you have to account for the kind of Frobenius twist on S. So one side will be kind of you kind of tensor with S, and the other side you tensor with a Frobenius twist. So implicitly, I'm going to be doing that later, but I'm going to be doing it cases where K is FP, and so you won't see the twist. But in general, you should remember the twist. Okay. Now, one more remark, and this is kind of the big remark. This is the whole point. Sense? Is that so in practice, I care about this in the situation where I start with let's say it this way. So X, so now not curly. So I start with some smooth proper scheme over WK, and Z is again a relative strict normal crossings divisor. And
Sorry.
yes.
Sorry. I'm confused. So what do you mean by a family version? Because I mean you define something smooth over WK, but in the family version was
So yeah, I didn't actually write this out. So maybe I should at least say. So if I tensor with S, then I'm going to consider pairs where I have, let's say S is an Eutherian.
No. I mean even what assumption on X on this curly X?
X is a smooth p-adic formal scheme over WK.
Yeah, but now you replace K by scheme.
So I'm going to tensor, I'm going to base change, I'm going to sort of multiply over spuff WK with this space. So imagine I do X times over WK with this space, Z times over WK with this base. Now I'm going to take a coherent sheaf on X times over WK with this base. And I'm going to still take the differentials relative to this base. So I'm not going to differentiate on the base. So I'm doing this in a kind of a base linear way.
Oh, so your X is still fixed. It's not a
Yeah. X and Z are still the same. And I just kind of multiply everything with a base. And I'm just parameterizing some family of objects in here. But it's not like a family with a connection or anything. It's just an algebraic family, formal algebraic. Yeah. Do that. Okay. Okay. So Okay, so now I'm going to assume that these things are just the p-adic completions of curly x and the curly g are just completions. And now, formal Gaga theorem says that if I define the family of connections, I kind of define modules with integrable connections in the analogous way on x comma z, then this is equivalent to doing it on here. So write so coherent sheaves, of course, are the same. You have to think a little bit about connections because it's not immediately obvious how Gaga applies in this situation. But if you think of this connection as a splitting of the first jet bundle, then kind of that makes it clear that you have objects that are algebraic and you're defining a formal morphism. So that morphism is also okay. So in this situation, you might encounter some object in, well, at least the isogeny category of this. And then so we can say like a Frobenius structure on some object. So now I'm going to write it without the fracture. Right, so in particular, because I have this equivalence, this functor that I'm talking about actually makes sense on this category. Now it's kind of mysterious because the proof of it, I mean, the construction of this functor is very much goes through formal schemes, but nonetheless, you get a well-defined answer. Of course, I should maybe remark, you don't necessarily get an, apropos of my previous remark, if you make an algebraic family of things here, you don't necessarily get a morphism on that algebraic thing because that remark really lives in the formal world. But at least if you have an individual module with connection on this scheme, then Gaga tells you that you know what it makes sense to interpret the result of this functor as another object. So an algebraic Frobenius structure on this thing will be an isogeny between E, well, let's see, some Frobenius pullback at E and E. So isogeny meaning kernel and co-kernel are killed by some power of P. P isogeny. So the kernel and the co-kernel have to be killed by some power of P, but the point is that in general, it won't be an isomorphism because I'm kind of working with integral structures. And classically Frobenius structures that you see coming from geometry, they don't act integrally. They act with some elementary divisors which have to do with Hodge polygons. So this is usually not an isomorphism. See that we'll see that in the next example. So these things typically exist for some sort of geometric reason. But you have to be a little bit careful. It has such a structure, if E has a sort of geometric origin, then you will have this structure for kind of reasons to do with crystalline Rham comparison. But that's already true if E has geometric origin mod P. Yes.
An actual map that isn't a certainty or a map?
Yeah, let's say an actual map that's an isogeny. Yeah, because that's, I'm just making a definition, so, but let's say, an actual map that's an isogeny. If I wanted to be casual about twists, I would. So, right, if E has a geometric origin mod P, then you get some structure like this from the Rham crystalline comparison. Fits my 30-year cutoff. Right. But it doesn't say anything about whether he has geometric origin kind of integrally, kind of up in characteristic 0. There's no obvious reason why we would expect that. But here's the situation I actually care about. And here the answer might be different. What if this whole thing comes from a number field? So suppose now, what if xz is the base change of x naught z naught times over f with say OFS WK, where F is some number field, S is some finite set of places, and W, and now K is a finite field, so WK is the completion of this thing with respect to some place. Lambda is a place not an S. So what if I actually got the situation from a number field? Then you can kind of ask, and I have no idea, does the existence of a Frobenius structure say anything about geometric origin? Or, this is a much less ambitious question, even about the existence of other Frobenius structures. Right? If I have some connection that really lives in geometry and characteristic 0, then it won't have a single of crystalline Frobenius. It'll have lots of them from almost all but finitely many primes. And so, is it the case that having one of these Frobenius structures is such a strong condition that it says something about other primes? So the meta question here is sort of how do different primes interact? So far P has been fixed, but I'm kind of opening the door a little bit and asking about different primes. Yes.
I'm sorry. What is the question? You have a.
So for example, let's make a concrete question. I start with this pair over a number field. And I give you a connection on it that when you base change to the completion at some place has a Frobenius structure.
And that's the question.
And the question is, does that imply that for, all but finitely many other places, you also get a Frobenius structure there? So, maybe the answer is trivially no, but maybe there's some, I deliberately didn't state a precise question because I don't know exactly what the precise question should be.
The general conjecture is that if you have a Frobenius structure almost everywhere, then it comes from geometry.
Yeah, so maybe you can ask, like, if you have these things for some thin subset of primes, but maybe positive density or something, does that imply all of them? That may be a less ridiculous conjecture. Because I guess I already it might be that even a single Frobenius structure is not enough to work with because it really only tells you about mod p. Yeah, but maybe you have infinitely many, and then maybe that tells you more. I don't think anything is really. I mean, maybe there are some results you could try to stuff into this framework, and that would actually be an interesting thing to do. But what I want to do in the remaining time is kind of mention two examples of families of connections where I understand what this Frobenius structure is, and it illustrates some features that may or may not generalize. So again, the purpose of this talk is to kind of provoke discussion more so than to actually achieve any specific result. Part two. So this is the example I advertised in the abstract. I have to say that the abstracts were due a long time ago. So when I conceived of this talk, I only had this one example. I want to tell you about another one as well. So go through this a little quicker than otherwise. So what is a hypergeometric connection? Well, so a hypergeometric connection is defined in terms of two families of parameters, which in practice I want to be rational numbers. But for the purposes of kind of formulating a statement compatible with this, these you might imagine allow these to be p-adic. But for the moment, they just live in some unspecified ring. Let's say these live in some ring. Specify later. So you define. So one way to kind of define a hypergeometric connection is to first define a hypergeometric differential operator. So this is going to be an order n differential operator on the natural place that it acts on is a Laurent polynomial ring over R, where you also invert z minus 1. So it's, and this thing carries the derivation z times d dz. So I'm going to write it in terms of, that's a first order differential operator. So it's going to be a degree n polynomial in this thing with coefficients in this ring. So it's the product of two monomials. So it's quite simple in that sense. Non-technical sense. So I have a product of d shifted by one set of indices, and then I have a product of d shifted by another set of indices, and this one is multiplied by the z. So the reason I inverted z minus 1 is because the leading coefficient here is z minus 1. So I really, if I want this to be monic, I would have to divide by that. So it's natural to invert z minus 1 right now. This because when you convert this thing into a geometric object, you get a connection with poles at 0, 1, and infinity. This corresponds to rank and connection on the P1R minus the sections 0, 1, and infinity, which I'll call this kind of bundle with connection E alpha. I guess I want to be able to do this integrally. So I mean, the conversion is kind of a thing you teach in ordinary differential equations. I don't want to kind of sweat too much time on the board with it. But right, if you have a differential operator of rank n, you can make a connection whose horizontal sections corresponds to a solution of this differential equation and its partial derivative and its sorry, it's d derivatives up to n minus 1, up to the last one that's not redundant. So you can convert this thing into a Rankine connection, and it'll be regular at these points, meaning it has only log type poles, dz over z at 0, for example. And because this thing is so simple, you can kind of do this in families. And so you can imagine doing this over you could take, for example, the formal affine space over ZP and these two n variables. So let me formalize this over the if I take x to be p1, say ZP, z equals 0, 1, and infinity, and I take the base in that sense to be so I take the formal affine space, the alphas and betas, then I claim there's a p-isogeny between, I can tell you what the Frobenius pullback of this connection is up to isogeny. It will be the thing you get by multiplying the exponents by p, by the alpha and the beta function. And this is some souped up way of exercising the fact that these 3-point connections of this form are rigid. They're kind of uniquely determined by their residues, which is not a general fact about connections on P1 with more singularities. So kind of this algebraic Frobenius pullback, you can look what it does to residues by kind of taking a connection, taking a Frobenius lift that preserves 0, for example. Then you can see that you're multiplying all the residues, you're multiplying the residue map by P at each of the singularities. So in particular, you're multiplying the eigenvalues of that map by P. And this is why you actually only get an isogeny, because here you're also multiplying the eigenvalues by P, but the residue is not 0 mod P, it's only nilpotent. So you have to kind of do some p-isogeny to kind of make things match up at the integral level. But you can control, but the co-kernel is you can make this injective with the co-kernel killed by p to the n minus 1. So. And I should mention, you can make this quite explicit using some work of Dwork. So my 30-year cutoff comes from the fact that Dwork wrote a book in the early 1990s summarizing some things that had gone on in theory of p-adic differential equations before that, where he explains how to write down this kind of isomorphism. He doesn't use this algebraic language, and he's thinking of the alphas and betas as being elements of ZP, but he kind of gives you a formula that you can that achieves this goal. So you can make that pretty explicit. Then what can you do with that? So now let me go to the case that I actually care about, where let's say these are rational numbers, and to make this connection irreducible, I need to assume that no alpha coincides with a beta modulo z. Right, these things only, the point is that if I take E alpha beta and I invert P, so I base change to a place where P is inverted. So now so this is like the analog of the curly E thing, but this is going to be a connection on P1 of let's say Q. So I use the same notion of making a connection, but now I make it on P1Q. This thing only depends on, well, it's invariant under the action of the permutations of the two sets of indices and integer shifts. So the integer shifts is the more interesting part. It's because because I have a regular connection, everything is really only determined by kind of e to the 2 pi I of the residue matrix. So integer shifts kind of disappear from the monodromy representation. So that's a statement over C, but you can kind of make that algebraic to whatever Q. And so you can then kind of compute explicitly an isomorphism, right? Because if I multiply these indices by enough powers of P, I will get something back that looks the same modulo integers. I mean, it might not be P on the nose, but some power, right? If you look at the common denominators and you take a power P that's 1 modulo that common denominator, oh, sorry, I need to assume that these things are p-adically integral. So you can kind of write down this isomorphism pretty concretely. Again, this is not guaranteed to preserve P integral structure, because when you do these integer shifts, you might pass through some situation where, I mean, you might have some things, you might have some pair alpha and beta that are not, they don't differ by an integer, but they're congruent mod P, something. That might cause some problems. But I didn't actually check what's going on here. I mean, it might be that these things actually turn out to be integral. I didn't check. Still working on that. But at the rational level, you could compute this explicit isomorphism. So I'll mention that. So in principle, you could, use this to compute Frobenius traces for, the resulting motive here. So for that, you need to somehow actually kind of go into the weeds here and figure out, at some point, how this thing actually is identified with a local Frobenius pullback. So that's not an algebraic step. So there is a step here that still involves some analysis, but in principle, you could kind of work out. So I say in principle because I haven't done this step yet, but in principle, you could use this point of view to recover the formula for these hypergeometric traces you find in Katz's book on exponential sums. And better yet, because this thing that Dwork did is more general, it actually works in what nowadays called hypergeometric systems. This terminology didn't quite exist when Dwork's book was written, because it was written sort of in parallel with the book of Gelfand, Kapranov, Zelevinsky. Maybe this book existed in Russian, but the English translation wasn't available. But anyway, so Dwork's construction works at this kind of, so these hypergeometric systems are some sort of connections on some toric variety with some poles. They're a kind of vast generalization of this hypergeometric setup. And I mention these because they make the following remark much richer.
Sorry, can I add something?
Yes, go ahead.
So this isomorphism that you write down here, so those are all, like this Frobenius pullback is only after pulling back to the
Yeah. So this Frobenius pullback is a p-adic thing.
Okay, and
This sort of thing happens over Q, but the Frobenius pullback is a purely p-adic thing.
and also like in your previous propagation, like do you have a natural identification between this E of alpha beta and E of P alpha beta after invariant P?
No, I mean, I only have this. I mean, E alpha beta, I mean, in general, oh, you mean if I'm assuming these things are? No, right, because I mean, alpha and beta, I mean, I could choose some set of rational numbers such that P alpha, P beta aren't congruent to these modulo Z, right? There'll be some, right, if I, yeah, like I might shift between something that's like 1 mod 3 and something that's 2 mod 3.
So that's not an F structure on E alpha beta. So because the target is actually not coming.
This one, well, you can think of this thing as pulling back, like there's a map from here to here, which is multiplication by P. So you can think of this as comparing this kind of weird pullback with a reasonable pullback on S. And that reasonable pullback is something that kind of, yeah, maybe I should actually, maybe this is actually going into my next remark. Right, this is a comparison of, FP star with a pullback on, so to speak, on the alpha beta space, which makes sense, which originates from Q, or maybe from Z. Right, it's the completion of some morphism that actually kind of in an obvious way was already defined over Z. And so, and those morphisms, right, multiplication by P on these things, well, if I take different primes, then I get a family, you get a family of morphisms on kind of the genuine affine space on these things. You get sort of genuine morphisms on this space that actually commute with each other. So the kind of provocative question is that, is there something like an R Frobenius in this context, in the sense of people who are not in this room? Is there some kind of, is this a situation where you can hope to have some kind of, one parameter flow that tells you something about the Hasave L functions? I have no idea. The point is that if you're looking for such a thing, okay, you could look at kind of silly situations like a single CM abelian variety where you kind of know the answer already. But this is a kind of non-silly situation because the motives that show up here have large monogermy group. It's just that this family somehow is quite well behaved. But for instance, one example of this is a Legendre family of elliptic curves. So you could kind of have a family that has all elliptic curves in it, rigidified by 2 torsions.
But can I still ask a little bit more? So,
yeah.
So how are those two isomorphisms related?
Well, this is right. This side is the pullback of my family by this base change on S. So it's whatever this. I mean, it's an isogeny, but this is expressing the relationship. So you could think of this as some kind of local reciprocity.
Is it true that if alpha and alpha prime differ by a bunch of integers, then you get the same?
Well, yeah. If alpha and alpha prime differ by integers, then there's an isomorphism you can make explicit between the connections you get in those cases. So I'm saying that if you can get this sort of thing by first, you pick your alpha and beta that are rational, you then, pick some evaluation point. You probably want some Frobenius lift, like Z goes to Z to the P and you take a fixed point of that. Then you figure out how the fiber at this thing actually is identified with the original, which is some analytic step, because, right, you have to actually go into the definition of this thing. And then you have this isomorphism, which is algebraic, and this isomorphism, which is algebraic. So you're kind of chaining 3 things along, but one of them is really p-adic in nature. But I've kind of isolated where the essential p-adic step is. It's in the identification of, it's in the interpretation of this side.
To compare things which differ by integers, we have to change the pole and the order of the pole and 0, 1, infinity also.
No, everything has a simple pole at 0, 1, or
Sorry.
everything is regular at 0, 1.
Yes, but
Yeah, you do some mirrormorphic. Yeah, you're doing something mirrormorphic there, but you kind of at the end you end up with something with a simple poles again.
A question.
Yes.
When you generalize to a hypergeometric systems, are you still over P1 or?
No, that's over some higher dimensional torque. Right. All right. So I only have a few minutes left, so I'd like to move on. We can have more questions afterwards. So I want to mention one other example, and I'm going to keep this brief because I only have 5 minutes. But I think it's important to include this example because it sort of shows the limitations of the previous example. So in this example, I take an elliptic curve over Q with good reduction at P. So I'm going to kind of consider not a genus 0 situation. And I want to look at the rank 1 connections. So these are parameterized on E. These are parameterized by a gadget called the universal vector extension. So it's an algebraic group that looks like this. It's E univ is, it maps to E and it's got a fiber which is GA, which is really some tangent space. But all I'm going to use here is that it's GA. And now I want to kind of apply this notion of an algebraic Frobenius structure in this situation. So I have to look at an integral version of this. So I'm going to sort of skip straight to what happens when you pass to generic fibers. So if I take the rigid analytification of this thing, this has a specialization map to the following thing. So I'm going to take E mod P, meaning I take the unique smooth model of this thing at P and I reduce down to get something over FP. I take the universal vector extension of that, and then I complete by throwing in, right? I have a GA bundle, so I kind of throw in the infinity section to get a P1 bundle. So points on here, I could also put the compactification here, but I'm only going to use this part. Points on here can be reduced mod P to land in here, and inside here, I take the pre-image. I take the points that don't reduce to infinity. So the picture here is that I have this GM bundle. So let's say this is the analytification. This is the analytification of E, and this U is some bundle and some disk bundle over this thing. It's trying to be sort of the disk bundle around the 0 section. This isn't, yeah, because I only locally have this geo structure. So, but this makes sense. This is some kind of model. And the point is that this is where the algebraic Frobenius structure will kind of carry this thing to itself, because this is where the connection is divisible by P. And I find this super interesting because I don't know why nobody ever told me this before, that, okay, in general, you don't have a Frobenius lift on the elliptic curve unless it's Cn. But this is a much weaker statement. This is saying that this kind of, I've got this sort of thickened version of the elliptic curve, and this thing is able to have a Frobenius on it.
What would reducing to the infinity section correspond to?
That's like imagine you're on the, so right, so this thing corresponds to, you have a rank 1 connection is a line bundle plus some connection on it. This is remembering what the line bundle is. Let's say I'm on the fiber over the trivial bundle. So then I'm specifying a connection, which is like specifying a differential. And this is like saying that this part is where that differential is actually, p-adically integral. And reducing to infinity is like it's not p-adically. So, right, so I don't get something defined on the whole space because this Frobenius pullback requires this kind of thing to be. I mean, it could be. It's defined on a slightly larger neighborhood than this, but this is good enough. This is what matches. This was what corresponds to the way I defined it. You can extend it a little bit. Yeah, and so the one comment I wanted to make about this, as time is expiring, is that if I take a prime that's not equal to p, then if I take this thing and look at the L torsion points, so the L torsion points in this group scheme, this is the same thing as L torsion points of E, because the fibers are GAs. So this thing acts on here, but that's, I mean, in some sense, that's not new information. That's just the action of, to identify this thing with group torsion. You can kind of think of this as being, it's not isomorphic. Relate this thing to EP mod L, and in some sense, this is compatible with the obvious Frobenius on this thing, because this thing is in characteristic P. But I mean, you can kind of make this more precise by saying, if I take Q bar here, except that it's not really Q bar, it's QP bar, and that's somehow the point. This is FP bar. Right, so now I can kind of relate these things as Galois modules. So this is somehow saying that this Frobenius that I constructed in a sort of de Rham way has something to do with the kind of étale Frobenius on mod L coefficients. So it's somehow saying that there's something that there's enough of a bridge here. The point is that these L torsion points actually live in this band. Of course, that's not true for L equals P. They're outside. For L not equal to P, they're kind of available, and I have this action on them, and it kind of agrees with this action. So I'm sort of writing down a de Rham interpretation of an étale thing, and the kind of provocative question, which I'll end with, but I'm not gonna try to answer. So, any questions about this have to be off recording. Does this have anything to do with Mochizuki's work on Spiro's conjecture, more in the direction of Spiro's conjecture? Because this setup looks a lot like what he calls Hodge-Arkelov theory for elliptic curves. So, as I said, I'm not going to claim anything like this, but this may or may not be motivation to think about these things. But I'll just point out that there's something maybe interesting going on here, but I'll leave it at that. Are there any questions? Yes.
You mentioned something about Hasse-Weil L functions. Could you sort of what sort of question might you ask? What the connection is between?
Well, I mean, the kind of crazy dream would be in some family of motives to write down some this kind of notion of an R Frobenius. I mean, some version of this has been kicking around a long time. The kind of fantasy is that something like even the Riemann zeta function sort of appears by you have some one parameter action of R on some topological R vector space, and then you can kind of differentiate to get an algebra action of the Lie algebra, and then that action is somehow the spectrum of that operator is somehow telling you this arithmetic L function. So that's kind of the fantasy that this is, and I'm not saying that this is actually any direct application to that fantasy. In fact, I'd be a little surprised, you know. But that's the kind of pie in the sky motivation.
So-
What I'm really looking for is some kind of concrete things that mimic that fantasy, but or maybe not completely concentrated. Sorry, but somebody else.
So it seems that from your equation that what you actually need is something like divided power structure on the base.
Oh, you mean yeah, I mean, that's somehow, I'm able to gloss over this when P is greater than 2 because, you know,
Yeah, so-
P has divided powers in the ring ZP. So,
Right,
but
so-
yes, that's what I would, yeah, I don't know whether this story gets more interesting if you think about divided powers, all the way over the integers, and then you can kind of try to play some similar games.
I mean, like, could you also like what part of your theory also works when this WK is replaced by some slightly ramified thing?
Well, if the ramification index is less than P minus 1, then nothing much changes. That's of course where P equals 2 breaks down. I should point out that of course, as long as the space is, not too ramified, your base space can be the parameter space, if you have a family, can be whatever it wants. But yeah, in terms of making the underlying space more ramified, yeah, once you cross that threshold of P minus 1, then you need kind of to do something more complicated. For example, this full faithfulness property will no longer be tenable. Because you can have a rank 1 connection of order P, pull it back, probably this. Yes.
Can there be like multiple different algebraic Frobenius structures sort of happening in the same context?
You mean we're a single prime P or?
Yeah.
That seems unlikely. It should be that this is, well, I guess in the sense that, yes, in the sense that if you start with something over a number field, it might have multiple places. And then you can complete at those multiple places, and then you really do have distinct Frobenius maps that a priori don't know how to talk to each other.
But it is single place. Do you have one?
No, at a single place, I think everything is kind of well defined.
Any other questions?
Just to follow up, I think the question is asking for a single vector boundary connection, can you have 2 Frobenius structures?
Oh, a priori, yes. I mean, in the examples I was looking at, I'm kind of thinking about cases where this thing is absolutely irreducible. So if you have an absolutely irreducible connection, then the Frobenius pullback will again be absolutely irreducible by this comment I made at the beginning. And then, the map between them, if there is a map between them, then there can only be one up to scalars. So mostly I want to think about that kind of situation. There's the only possible ambiguity is just a limitation.
So maybe a really naive question. Maybe in an attempt to eliminate some of the arithmetic complexity of what you're talking about, have you tried sort of setting up a similar conjecture or meta conjecture in the case of a function field?
In the case of a function field, somehow it feels like probably things are too easy. But I guess the point is that you could tell whether, yeah, I don't know. I don't know what I can sort of infer from the function field case. I feel like I'm likely to go astray if I do that.
Towards the end of the talk, you explained how these algebraic Frobenius structures come up in contexts involving italical homology.
in this one example, I see that. I don't know if that's if there's anything general going on here.
Could that have something to do with some kind of Riemann-Hilbert correspondence?
Possibly, but the role of this prime not equal to P, I don't really understand. So I guess my short answer is I don't know.
So what kind of information do you get about a hypergeometric systems from this kind of?
Well, you again get the fact that when you have rational parameters, that there are Frobenius structures for all primes p, where the power depends on the residue of p modulo some integer. So really everything is living over some cyclotomic field in general. So you have some motive over a cyclotomic field, and you're getting kind of explicit formulas for its Frobenius traces, which, by the way, are things that are probably quite computable. In the kind of classical hypergeometric case, I have very efficient code for computing these Frobenius traces. So it's actually a kind of interesting problem from a computation. I'm happy to answer more questions, but I feel like we should probably get some lunch.